Right, so another form of a trig equation for you that we need to solve. And this one's a little bit more complicated, and the main thing about this is that it is different to the previous ones. And if you look at the title at the top, it's a cos x plus b sine x plus c. So there's no cos squared x's, there's no sine squared x's, there's no sine 2x's, and there's no cos 2x's. There's not even a tan x that we could take out. So the idea is that the only replacement that we know for cos x is something involving tan x and sine x, and likewise for sine x it would be cos x and tan x. So by substituting them out, we're not actually gaining anything. So the point of this question is to change it into something that kind of gets rid of one or the other, and the only way we can actually do that is through what we know about the wave function. Okay, so in terms of unit 1, we looked at the wave function, and we looked at the different ways of changing something like this. It didn't involve the c, and the c generally comes in the second part of the question. And that's the main thing I think to take from these questions, is that these generally would be a two-parter, and the first part would just look like an ordinary wave function question, and then the second part would be hence solve for something or other. We actually kind of touched on this in unit 1 as well, but it's just making sure that you understand the difference between this and the ones that we've just recently done. So there's nothing else we can really do, as I say, when it's in this form, apart from use what we know about the wave function. But the main difficulty comes, and I don't necessarily know that the SQA would ever do this, because this is adding a little bit more difficulty than is required, is that it might not tell you the form that they want you to put it in. So generally with a wave function question, they say write in the form k cos x plus alpha, or whatever it is. If they don't actually tell you that, then you have to select one for yourself. Okay, so it would be one of the following ones, and they're just the four formulas that you get in your formula sheet. Obviously, they're combined in your formula sheet. You got the sine ones together and the cos ones together. But you might have to select one of them based on the function that you have in the first instance. We'll get to one of these in a second. Don't worry about it too much. As I say, I don't think you'd ever get a question like this. It's more the second part that we want to look at anyway, but we need to kind of remind ourselves about the wave function first of all. So an example for you. So we're going to rewrite 5 cos x plus 12 sin x in the form k cos x minus alpha, where k is greater than 0 and alpha is between 0 and 360. So that's just kind of the housekeeping parts of the question. We know k is a positive number. At the end of the day, we square root it to find k. So it just eliminates the fact that one of them could be negative. So it's just the fact that there are two answers to the solution that we find, but we just want the positive one. And the fact that alpha is between 0 and 360. Obviously, this is a cos. This is a trig equation in part, and there are unlimited answers to the trig equation unless we have a range like this, okay, an interval like this, sorry. Okay, but nonetheless, this first part is just a trig equation question, so we just got to remind ourselves of what we're doing here. But basically, if we're trying to write it in k cos x minus alpha, we need to expand k cos x minus alpha, and just be very aware of the fact, yeah, don't worry about that. The second part, the cos x minus alpha, if I go back a little bit, the cos x minus alpha bit is just from your formula sheet, so you can expand that easy enough. Just remember when it's cos and when it's negative, when you expand it, it becomes positive. And just remember when you multiply through by the k, it's both sides that get multiplied by k, okay? And then once you've got to that stage, it's just a case of matching it up to what we started with. So we've got 5 cos x plus 12 sin x, and we now want to rewrite that in this form. So there's a lot of similarities here, and we just want to find those similarities. Remember, this is just equating coefficients. So we've got a cos x on both sides, and basically what we're multiplying the cos x by on both sides will also be the same. So we've got 5 on this side times by the cos x, and we've got k cos alpha on this side multiplied by the cos x, in which case we can say that k cos alpha must equal 5. Likewise with the sin x, we've got sin x on both sides. On the left it's multiplied by 12, on the right it's multiplied by k sine alpha, so we can say that k sine alpha equals 12. Right, don't take that for granted. I think I've seen in a couple of your homeworks that there's a lot of you just writing that down. Look at it carefully, because with the different formulas it changes around. You need to look at that in a bit more detail, okay? So you have to write them explicitly for your exam kind of situation, and this is just, and they don't actually do anything as they are, but they allow us to find both k and alpha. Okay, so start by finding k. Just remember that k is equal to the square root of your a squared plus b squared, when k cos alpha equals a and k sine alpha equals b. You don't need to write any of that. It's just a reminder of where this came from. Okay, but the idea is it's basically just a kind of a Pythagoras based question. It's 5 squared plus 12 squared, all square rooted. 5 squared is 25, 12 squared is 144, add them together, you get 169. The square root of that is 13. As I say, it's plus or minus 13, but because we know k is greater than 0, it must be the positive version. Okay, so k is 13, that one's sorted. And then it's just the same kind of idea as before in terms of finding alpha. Okay, so in terms of connecting these two, we want to do an equation that involves the two of them. So we know that tan alpha equals sine alpha over cos alpha. In other words, the k's would cancel out, in which case tan alpha would equal 12 over 5, in which case alpha would equal the inverse tan of 12 over 5. Shove that in a calculator, it's 67.4. You do need a cast diagram. I have no idea why this is all jumbled up, but you're in the A quadrant, and because it's because it was positive cos in the first instance, okay, you're in A and C, and then we need to look at the sign as well. That means we're in A and S, in which case we've got 2 ticks in A, so that must mean we're in the first quadrant. And often you are, but don't take that for granted. Again, if one of these is negative, then you won't be in that first quadrant. So you do have to look at this in the same way you do have to look at these in more detail. Don't just take it for granted what's going to happen here. Okay, look at it in more detail, do the work, and make sure you get the right answer. In which case we can pretty much write our final answer now, because if we're in the first quadrant, it is just 0 plus 67.4. Okay, so rewriting what we started with in this form, we've got our k is 13, we've got our alpha is 67.4. So 5 cos x plus 12 sin x equals 13 cos x minus 67.4. Okay, so that's the first part. That is just a wave function question. That was just from unit 1. But to do part B, it's slightly different. Okay, so we've got a couple of things going on here, and what you've got to spot here is the difference, or the similarities more importantly, between the first part. It says hence. Remember, as soon as you see something like hence, it probably means you have to use what you've done in part A. Okay, so we're looking at the connection, the similarities here. We've got 5 cos x plus 12 sin x. We've got 5 cos x plus 12 sin x in the first part, but we've got this minus 11 as well. Okay, and it equals 0, and we've got our limit again. Okay, so what we've got here is basically 5 cos x plus 12 sin x minus 11 equals 0. Okay, so that's what's happened in the second part. But we already know that 5 cos x plus 12 sin x equals 13 cos x minus 67.4. And the reason is that this is much easier to solve because there's not two x's. We've narrowed it down. We've taken this 2 parts in part A, and we've taken it into 1 and leaving us with just 1 x. It's much easier to solve that if that's the case. So however order you choose to do this in, we could have taken that and shoved it in straight away, but 5 cos x plus 12 sin x, when we move the 11 to the other side, in other words, add 11 to both sides, will equal 11, and then we substitute that in, we get 13 cos x minus 67.4 equals 11, okay? So what we found in the first bit, part A, is equal to 11, okay? And as I say, now we've got something that we can solve, and this is just going back to what we were solving at the start, okay? So trying to get x by itself, so basically I want to get rid of the 13, I want to get rid of the cos, and I want to get rid of the 67.4. But just remember when we're doing trig equations and we've got something like this, whether it be x minus or plus something, or 2x or 3x, we do that after, we'll deal with it after we've done the cast diagram and everything, okay? So start by moving the 13, okay? In this case, yeah, the limit's going to change, the interval's going to change, because we've got the x minus 67.4, these will obviously all change. So linking back to what we did at the very start of trig equations. But at the end of the day, you're going to have 2 answers, and you can just look at the answers. You don't get marks for doing this, but you've just got to know that if you kind of continue as is with this, and you ignore the kind of limits, what's going to happen is you're going to have one outside of this interval. So whether you look at the interval now or you look at the interval at the end, you do have to do it, and you do have to change your answers accordingly. And it can just be a case of adding or subtracting 360 to the one that's wrong. Okay, and I'll go through that in a bit more detail in a second. But a lot of you I know kind of like doing it this way, so just take care of it at this stage once we've got the fact that it's x minus 67.4 now instead of just x. Okay, right, so divide by 13, cos x minus 67.4 equals 11 over 13, and then we do the inverse cos of 11 divided by 13 to find the related angle, but remembering the fact that this is x minus 67.4. Okay, so that gives us 32.2. We've got a cast diagram at this stage. We've got cos, and it's positive, so we're in A and we're in C. Okay, in which case we've got 2 answers, which are for x minus 67.4. Okay, so once we've got the related angle, we're going back in and we're going to solve it for x, but it's not just x, it's x minus 67.4. In the first quadrant, 0 plus 32.2. In the last quadrant is 360 minus 32.2. So simplify them down a little bit, and then add the 67.4, okay? So we add the 67.4, we get 99.6 or 395.2. Right, what a lot of people do at this stage is just leave it. That's your answer. We found x, sweet. But the problem is this one is outside of our interval. 395.2 is out of our interval. Okay, so we do not want that one. But the point is, it doesn't just mean that this is the only one. It brings in, basically what's happened is the graph has shifted along to the right, okay, in which case the two solutions are that we've got a 99.6 or 395.2, but that's out of the interval that we want it to be. But because this 395.2 has been moved to the right out with our interval, what it's done is it's brought in another value from the left-hand side. So you can either be thinking in terms of your cast diagram, what that means is that there's one as a solution before in the quadrant before 0 plus. So what that means is there's a 0 minus, and you can add that on the end here and just do 0 minus 32.2, in which case it's minus 32.2, and add 67.4 to that. Or what you can think, like, because this one's gone out, another one will come in and it will happen 360 degrees earlier. So you can just take 360 degrees away from that. Either way, you get the two solutions of 99.6 or 35.2, okay? As I say, if we thought about it at this stage, the stage earlier, it would have been minus 32.2 would be one of our solutions that's in the interval that we've got here. And when we add the 67.4 to minus 32.2, we would get 35.2. Bottom line is you should have two solutions, okay? And the bottom line is they need to be in the interval that we're dealing with, okay? So however you get to them, just make sure they are in the interval and just yeah, make sure you do your corrections accordingly, okay? Right, I'll give you one more example, okay? So we're solving the equation this time. This is virtually the same. This is just going to involve a bit of radians, but this one goes straight in, okay? As I said, I don't think the SQA would do this. I think they're going to build you up in a two-part question, yeah, just in case, I'll show you this one. So we've got root 3 sine x minus cos x equal to 2, and we're trying to solve it. So if I went straight in and did this, you're perhaps thinking, first of all, in terms of what we've done in the last couple of lessons. So could I take out a sine x for something? Could I take a cos x out for something? And no, you can't really. Not that would help you anyway. If you take out a cos x, as I say, it would bring in a sine x and a tan x, or it would bring in, yeah, something entirely different. Nothing that's going to help you. You've just got to recognize that when you've just got a sine of a singular x and a cos of a singular x, it's the wave function that we need, in which case we need to basically match up with one of the following, okay? So we're looking here at which one's going to be the most appropriate for us, okay? It doesn't really matter. You'll get a correct answer at the end of the day. It just might be a bit more awkward, okay? But because we've got root 3 sine x minus cos x, what we basically want to make our life as easy as we can, we want a positive sine x on the left-hand side, and we want a negative cos x on the right-hand side. So you can see this bottom one is going to be the most useful, most easy for us to deal with, because it's going to minimize the use of negatives. But all of them would work, and you can just pick one at will. It doesn't really matter. But if you pick one willy-nilly, you're just going to have more negatives to deal with. And I know you all hate dealing with negatives. So if you give yourself kind of 10 seconds to think about it first, then this one would be the most appropriate, because you've got a sine x on the left-hand side that's positive, and you've got a cos x on the right-hand side that's negative. Okay. Right, so in which case we're going to rewrite it in k sine x cos alpha minus k cos x sine alpha, remembering what that actually initially started with. Okay, so we've got sine x, and we've got root 3 and k cos alpha, in which case k cos alpha equals root 3. And on the right hand side we've got a cos x and a cos x, and we've basically just got a 1 there, okay, and it's k sine alpha over there. So technically minus 1 equals minus k sine alpha, but if minus k sine alpha equals minus 1, then positive k sine alpha equals positive 1. Okay, so from there we can get our k value. It's root 3 squared plus 1 squared. Just be careful with something like root 3 squared. Root 3 squared is just 3. 1 squared is just 1. So this is a square root of 4, which is 2. And then alpha comes from doing the inverse tan of 1 over root 3. So remember, it's just sine over cos. So it's 1 over root 3, which is pi over 6. So again, because this is radians, there's no problem with you using degrees throughout this whole thing and changing to radians at the very, very end. I've shown you recently how to do that. Okay, at the very end, you just times by pi over 180, and you can write it in its simplest form as a fraction and just leave the pi as is, or you can literally times by 3.14. Okay. Either way, the inverse tan of 1 over root 3 is an exact value. It's 30 degrees or pi over 6. Okay. Right, so from there we can rewrite the original form. So just remember, that's the form that we use. We use sine x minus alpha, okay, in which case our k is 2 and our alpha is pi over 6. So this is the same as 2 sine x minus pi over 6, okay? Right, but the whole point of this question is to actually solve it. So we're going to take this root 3 sine x minus cos x equal to 2. We're going to replace the root 3 sine x minus cos x with what we found it's equal to and make that equal to 2. And this is something that we can solve, as it was in the first instance. We can't solve it because we've got sine x and a cos x. Now we've got just an x, we can solve this a lot more easily, okay? So just going through it as normal, divide both sides by 2, inverse sine of both sides, okay? But remember, this is the x minus pi over 6. This is the related angle that we're trying to find, okay? So we're going to have a cast diagram at this point, although my cast diagram seems to be in I haven't put it in at all. Okay, but anyway, at this point, the related angle is pi over 2, okay? So we've got a cast diagram, and because we've got sine that is positive, okay, we're in the first and the second quadrant. We're in A and we're in S. At the end of the day, because it's just 1, it's 90 degrees, it's pi over 2. So it's basically 0 plus pi over 6, and it's 180 minus pi over 6, in which case, no, that's not right. So sine x minus pi over 6 equals 1. So we're going to do the inverse sine of 1. And remember, that's our related angle. But if you actually think about this, because it's just 1, if you think about a sine graph, that's only at 90 degrees anyway. Okay, there's only one solution for this. Okay, so if we go through and we actually do this and we put it in a calculator, or we think about our exact values, we're doing the inverse sine of 1, which is 90 degrees, or pi over 2. Okay, so there is only one answer to this. So we don't necessarily need to do a cast diagram. If we did, it would be A and S. In which case it would be 0 plus 90 and 180 minus 90. Okay, either way, we just get an answer of 90. But then when we take into account the fact that we've got pi over 6, it would be 90, or pi over 2, plus pi over 6, which in its simplest form is 2 pi over 3. Okay, if you're going to add two fractions together, just remember you need the denominators the same. So this would become 3 pi over 6 plus pi over 6 would be 4 pi over 6, which simplifies to 2 pi over 3. Okay.